Hi guys. All right, today we're talking about work. So before we jump into work, I just wanted to review a little tiny bit of surface area, etc. So take a minute and let's pause the video and let's try this warm up. And then when we come back, I'll go over it and hopefully that'll answer any questions you have. So let's go ahead and hit pause now, and then we will come back and after you try this warm up. All right, I'm gonna pretend we're gonna go here. I'm gonna pretend that you guys all have done this warm up and it's beautiful. So let's look at this graph. 6x minus x squared. Hopefully I wrote it like I think I wrote it, which is we have this, this nice little parabola here. I just wanted to trap that area between that and the x-axis and then mess with some stuff. So this one is perimeter. So perimeter, remember, we need to use our arc length formula. But we don't want to forget the arc length is only going to give us this guy. And to close off our perimeter, we actually need this guy too. This guy's super easy because 0, 0, 6, 0. You could Pythagorean theorem it, whatnot. It's a straight line, left minus right. That's just 6. It's a horizontal line, so there's no slope even. Right? And then for our arc length piece, we're going to want to integrate from 0 to 6 of the square root of 1 plus our derivative squared. So 6 minus 2x, whole thing squared, dx. And then for our perimeter, we're going to need to add 6 to get our perimeter. So we're going to go ahead and put that integral into our calculator. So remember, we're using our math int. And then I thought I would just double check and make sure I get you a numeric answer to look at. So 1 plus the square root of 1 minus, 6 minus 2x, whole thing squared, dx. And that should give us that 19.494. And then we still need to add a 6 to that to get to our total perimeter of 25.494. And those would just be units since they didn't actually give us any units. Okay. Let me know if we have questions there. Now we're in surface area and we're taking that same region and we're going around the x-axis. So I always think it's good for us to think about our picture. This time we're going around the x-axis. It's this area in here that we're rotating. So my surface area is just going to be from this outside piece rotated around. Of course, remember for surface area, the surface area is the integral of r 2 pi r times our arc length. And r, this r right here, is the distance from our axis of rotation to our function that we are integrating, or to our edge, sort of, that we are rotating. So in that case, r is just going to be f of x minus 0. Whoops, not equal 0, but f of x minus 0, which is just, of course, f of x, or our 6x minus x squared. Which means that we get, for this one, for our surface area, 2 pi integral from 0 to 6 again, right? 0 to 6. R this time is that 6x minus x squared. And then we have the square root of 1 plus our derivative squared, which of course is that 6 minus 2x, whole thing squared, dx. So same thing, I just wanted to make sure that we get a numeric value and make sure that we have this correct. So let me go ahead and multiply that by, 6x minus x squared. And I believe, if I did everything right, we should get a surface area of 539.7347. So that's going to round to 73. Let me know if you have questions on either that arc length or surface area. Otherwise, let's jump into this volume. So this first one, this first one says the volume of solid forms when we take this region right here, same region, 0 to 6. And we're going around the line x equals 8. So x equals 8, that's a vertical line, right? So it's out here, x equals 8. And then, of course, this is our region that we want, okay? And if we are going around this vertical lines, remember, shell is usually a really good idea. And so we go, yeah, we can do a shell. This is R and this is H. So R is a right minus left situation. And R should always include our axis of rotation since it's measured from the axis of rotation. So in this case, R is going to be 8 minus X because wherever my little rectangle is just at the X value. Okay. And then of course, H is just top minus bottom, which is just f of x minus 0, which is really 6x minus x squared. And then, of course, for a shell, if we rotate this around, it makes a little tiny cylinder is the word I'm looking for. So 2 pi r h from 0 to 6, 8 minus x, and times 6x minus x squared. Not a terrible integral to do. Not a terribly exciting integral either, though. And so we're going to go ahead and use our calculators again, integrating this from 0 to 6. And make sure you use parentheses, like 8 minus x in parentheses, so that you don't mess up. And then, of course, I usually just store like that equation in my y1 so that I don't have to keep typing it over. 1130. I got 973. Hopefully you guys are getting the same numbers. All right, last volume one I wanted to do today was similar, but this time we're going to take this guy from 0, 0 to 0. This maximum is actually here at 390. That's not super duper important. What's important is that this line y equals 10 is above and it doesn't intersect. So now when we take this guy and we rotate it around that line up there at y equals 10, then we can see, here's our radius coming off of our axis of rotation. This is a big R and a little r situation. So big R is going to be our axis of rotation minus the bottom. In this case, because the bottom is further from our axis of rotation. And little r is going to be our axis of rotation minus the top function, right? Because that produces a smaller radius. So the bottom is super boring because that's y equals 0. So big R actually becomes 10 minus 0, which is just 10. Little r is much more exciting because it's changing, right? Here little r is very big, here little r is small, back here it's big again, okay? So little r is that top minus 6x minus 6 squared, which little r I'm going to write a little bit cleaner as 10 minus 6x plus x squared to make my life easier. Or you can think of it as like your 10 minus 101. But in any case, we should be recognizing that this is a washer, so we need to set it up in sort of that area minus area situation. So like pi r squared minus pi little r squared. So we have pi integral from 0 to 6, big R squared of 10 minus little r squared of 10 minus 6x plus x squared, because I went ahead and distributed squared dx. So let's go ahead and do that. So pi times the integral from 0 to 6 of our big radius squared minus our little radius squared. Oh gosh, I pushed all the wrong buttons in my calculator. Let me finish typing that. All right, times my little radius squared. There we go. Oh, and I guess it doesn't work if I don't tell it dx because it's got a day. And so I got this total volume to be 1447.64589. So I'm going to round to 646. All right. Hopefully that's one more help with our volume, and that helps us a little bit. Let me know if you guys have questions or something is not making sense. All right. Then, if we don't have other questions, we're going to move into what we're talking about today, which is just another application. But this time, our application is work. So, work in physics is force times distance, okay? And so, usually in English units, a force we're thinking of is like a weight. So, usually in English, we're hearing pounds, okay? So pounds times feet, because it's a weight times or it's a force times a distance, and then and weight is not really a proper force, but pounds are a force in physics, right? So pounds times feet, so they call it foot pounds, is our exciting name, and the metric units are Newton joules, right? No, Newton meters, which are joules. That's what it is. So a Newton meter is just moving 1 Newton, 1 meter. And remember, Newton is your units of force from physics. So this is our force, and this is our distance. Okay. So one thing that's important about physics, it's a little bit weird, is we have our little 6-pound box that comes down the conveyor belt to this dude. His work is only moving the 6 pounds in a vertical direction. So only this vertical part is work. Physics is just funny like that. I don't have a good reason why. So if he had to move this 6-pound box up 5 feet, then he moved 6 times 5, or he did 30 foot-pounds of work. Okay. And then, of course, we can think of it in all these other ones. This little one comes down 4 pounds. If I set that up 5 feet, then that one is going to take 4 times 5, or 20 foot-pounds. Okay, and then I think I had one more example. So if I move my 1 little pound up 5 feet, then that is, of course, 5 foot-pounds, because I moved 1 pound 5 feet. So just quick review on work, because where we're going with this is, of course, needing to use it to take integrals. One more thing before we dive into this is, what weighs more, a pound of feathers or a pound of lead? And of course, they weigh the same, but they have very different volumes because they have very different densities. Okay, so sometimes density comes in. And so that's where we're going, is we're going to be doing stuff using densities. So let's keep getting into it. So if you guys remember, density is mass times volume. There's actually this other density that we're going to use, which is called a weight density, where it's just a weight divided by volume. So it's called a weight density. And this is great because this weight is going to put us into the force land so that we can start getting our so force, of course, we know the force to lift something is called its weight, right? That's sort of the idea behind pounds in the English versus our mass. And so what we do to find our force is we take our density times our volume, because I told you, oops, I haven't helped by the pen. I told you that how weight is force, right? So basically what I'm saying is we're turning weight into force, okay? And then when I solve this for force, then I get that's my density times my volume. So where we're going with this is we are going to basically figure out what is my little tiny force that I have and how far do I have to move it. And then we are going to accumulate those expressions. So of course you guys know accumulate by now means integrate. So let's I think that where I have next is a example. But let me dive into this volume just a tiny bit more. Because the volume's actually where our dx or our dx or dy, depending on what we're doing, is going to show up. We use dy a lot here because we're moving things in a vertical direction, so y ends up being our variable. But it's really just because we're moving in the y direction, and it's not like we need to rewire our brains like when we were doing just the volume of something. So where we're going with this is I mentioned that work, oops, would help if I had a pen, I'm sorry. Work equals force times distance, right? And then I said we're going to split this force up as our, goodness, I can't even write today, as our rho, which is density. This little letter that looks kind of like a P, it's called rho. It's a Greek letter, and it usually stands for density. And then our volume is going to be the area of a slice, like a cross section. And then we're going to have our distance in here still. But this area of a slice isn't a volume yet. So that's where our dy comes in to create, that's like the width of each slice. And then we just integrate from something to something. Okay? So let's kind of explore this. So with some numbers, I think it makes so much more sense than when we're stuck in this land of pure variables. So let's look at some examples, and then we'll have some more practice tonight. So here we go. We have a rectangular tank. That was very nice of them to start us off with a rectangular tank. And its base is 19 feet by 17 feet. So let me draw that in. So this is 19 feet, and this is 17 feet, and it's 10 feet. And it's just full of water. Now this part right here, the water weighs 62.305 pounds per cubic foot. That's our weight density. 62.305 pounds per cubic foot. Okay. And so we see, oh, look, if we multiply this by volume, we'll just be left with pounds. Okay. So now the water must be pumped to the top of the tank. And so we're lifting the water up to here, to right here. So water has to be moved up to here. So we're going from a depth of 9 feet to a depth of 6 feet. So here's our light, say 9 feet. And here's our 6 feet. Imagining. Okay. So here's what we usually do. We think of it like here's our axis, and this bottom of our tank is generally where y equals 0 is. Okay. So how high up I am is y, with like specific points being I'm gonna move from 6 to 9. Or out of the tank from depth of 9 to 6. So then what we're going to do is we want to do our rho times our area times our distance. Okay. So the area is like I take this one tiny little thin slice out of here. Now this one tiny little thin slice is 19 by 17 with a width of dy. So the area of each little thing is 19 times 17, okay? Now the distance that I have to move it, is I have to lift it from here up to the top of the tank. So at 9, you guys see I have to move it only 1 foot up to 10. When I'm down here at 6, though, I have to move it 4 feet up to 10. So remember, the height I'm at any given moment in time is y. The height I need to lift it to is 10. So to get from y to 10, whoops, I was going to write the number 10. From y to 10, I need to move by 10 minus y, right? So if y is like 5, I would need to move 5. If y is like 4, I would need to move 6. If y is like 8, then I only need to move 2. So this 10 minus y is my distance. Which means when we set up the whole problem, we said work equals force times distance. And my force is variable because, well, my distance is moving, but my force is not variable here, I guess. Force is relatively okay here. My force is my rho times my area times the dy to make it volume. So force, remember, is rho times volume. Okay, and this distance we said was 10 minus y. So that means our work is the integral from 6 to 9 of rho, because rho is a constant, area, 19 by 17, which is very boring and not changing, the distance, and the dy to make it into an area. And then, of course, rho, I think, was like 62.305. So we would go 62.305, 6 to 9, y. And then we can just put this into our calculator. With all of these, I'm just assuming that you guys are putting them into your calculator in general. Not that this would be a difficult integral to do by hand, and you should certainly be able to do this one by hand because you're just integrating 10 minus y. But our numbers usually get pretty big and ugly pretty fast. So I got 1, 5, 9, 3, 3, 4, 8, 6, 2, 5. And that would be okay. Foot pounds because remember rho was gosh, what was it? Pounds per feet cubed. So then the 17 feet and the 19 feet, they canceled and canceled. And then the distance that it moved adds another feet, and then this dy is the last place where that sort of foot comes in. All right, let's try another one. So this time we have the same tank. This time they gave us the answer. Let's find out if I'm right or not. And it still has a height of 10. This is 17, this is 10. And the water still weighs at 62.305 pounds per cubic foot. And this time we want to go from 6 feet to 3 feet. So it's the same idea. All that has happened to us is they have changed our limits of integration. So these depths are telling us our limits of integration. So work is force times distance. So from 3, I guess I should have had you guys try this one before I just blasted into it, but you'll be okay. I always need that rho. I'm going to put rho out in front because rho is obviously a constant. So here's my area. The dy, I'll make that into a volume. And then I need to think about what's my distance. So then I have density times volume, and it's a weight density, so it gives me a force, my distance. How high do I need to lift each slice? Because I have to go up to the top of the tank. So that's 10 minus y again. So let's see if we did this right. And we get the right answer by plugging it into our calculator. So go ahead and drop it in your calculator. You should get the same thing. as well. I mean, not the same thing, but the same is what they put at the top of our paper, which is that 332,054 because it's like 0.49. Okay, and that is again foot-pounds. Let's try. I think I have. What do I have for you? Let me see. Let's try one more. And looking at this one, I have like 2 more questions for you, but this one, why don't you go ahead and pause the video? It's the same idea, but let's go ahead and pause the video and try this one. So hopefully tonight on your homework, it'll be, well, I know it's less boring, but we have a lot of these that generally just start out as sort of our rectangular tanks, right? 19 by 17 by 10. Go ahead and draw it in because then you'll see. I like to draw my little water line, and sometimes I just label that as Y. Now, I know I want to go from 3 to 0. So, and sometimes I'll put that in my picture, like from Y equals 3 to Y equals 0 is what I want to do. But usually this depth stuff, I just collect that information because I know it's going to be my limits of integration. We always need rho density, right? Pounds per cubic foot. Per cubic foot should remind you you need volume. So I need to think about the volume of a little cross section. So these are nice because it's a rectangle. So the cross-sectional area doesn't change. If we had some weird shape, we might have, oh my goodness, what in the world did I do? I'm so sorry. I'll figure this out someday. Okay, if we had like a not rectangular tank, like a trapezoidal tank, these could be changing. As long as we have like a nice rectangular tank, then it's going to be constant. Think about like your related rates. The distance we need to move. Since we're still forced out the top of the tank, it's still at 10 minus y. If we were going just out the bottom of the tank, then when I'm right here at 3, I just need to move it down 3 to the bottom, so it would just be y. In this case, it's 10 minus y. Then, of course, we need our dy to complete our volume. Use our distance. And then the rho plus the volume makes our force, which is what we get, force times distance. So hopefully, when you integrate that, you should get the right answer from the top of the page, which was that 513,174. I got 175 when I did it in my calculator. We won't judge. There was some rounding error there on someone's part. I'm not going to take the blame for it. I'm going to throw that on the computer there. Okay, and that is, again, foot-pounds. I'm not too worried about being off by 1 on that many significant digits. So, you might wonder, why are our answers not the same? In this first one, if you look back, we went from 9 to 6, and we lifted this water up to the top of the tank. In the second one, we went from 6 down to 3, and then we lifted this water out of the top of the tank. And then in the last one, we went from 0 to 3, and then we lifted this water out of the top of the tank. So hopefully the picture gives you the insight that we are moving the water different distances. And since we're moving the water different distances, then it's going to be more work for a further distance, right? It's much more difficult to pick something up over your head than just up to your waist. So think about not only do we have how much we're moving, but we also have how far we're moving. All right. Well, then with that, I'm going to go send you guys off. Try your problem set. Now, I'm pretty sure this problem set goes up to number 7, but number 7, don't do tonight. Just save that for later. But just try 1 through 6. They should be all volume. And let me know if you guys have questions.